Okay, so the biggest thing is tomorrow is the lab test. Um, and so for that, you just need to be able to do questions like were asked on the labs, um, not including uh, not including the stuff we did last week that was the review for circular motion. Um, Question? Yeah, that kind of stuff. So figuring out what direction. So looking at a position versus time graph in 1D, is the thing speeding up, slowing down, going in the positive direction, negative direction, and then, like you said, looking at the path, uh, figuring out what you know about the direction of the acceleration, the direction of the velocity, that kind of stuff. Okay, so what I would do is just glance back at the labs. I mean, depending on how solid you are on it now, it could take different amounts of preparation for different people, I suppose. But look back at the labs and just go over the questions and just ask yourself, do I remember how to answer this? And if you do, then you probably don't have to spend a lot of time getting ready. Um, all the lab exams together add up to 10% of your grade. So this is 3 1/3% of your grade. So don't kill yourself over it, but little by little, we're just trying to put all these ideas together. Any other questions about the lab test? Okay. So we're going back to particle kinetics. And here's what we've talked about so far. The force types are first the field forces. And for that one, all that we're talking about for now is gravitational force. So the gravitational force is mg down. Okay, and that's all you need to know about it. And then once you've dealt with the weight force, the gravity, then you have to deal with the contact forces. And there are 4 of these that we're going to do in this class. There's pushing contact, pulling contact, friction, and then force applied by springs, which, like I mentioned last time, is really just here because it's an introduction to elasticity, which is going to be a big deal. We've basically talked about this. We haven't done any example problems, but now we're going on to pulling, and I'm going to finish talking about pulling, and then we'll do a bunch of example problems, because I think once we've done pushing and pulling, you can do like the first 19 questions in the kinetics homework, so that's a good place to stop and step back and kind of solidify stuff once we get done with that. So, okay, we're going on to this now. So pulling contact force. I think the easiest way to think of what is a pulling contact force is, well, the way I talked about a pushing contact force was like it was a force that prevented two objects from merging, you know. It's the force that gives things its own space. Pulling prevents something from escaping. Um, but I think there's an easier way to think about it than that. Um, a pulling force is one that could be applied by a cable. So if you try to push on something with a string, the string is just going to compress and you won't get any, much at least, force depending on how thick it is. You know, to us, cables and strings can't apply any pushing force mathematically. That's how we treat them. So if you imagine this force, this contact force being replaced by a string or a cable, and everything still works the way it did originally, then that's a pulling force. If you imagine that, and what would happen is that the string would just compress and no force would be applied, then that's a pushing force. And so to figure out the direction of this force, imagine that contact being replaced by a cable. Most of the time, it actually will be a cable that's applying this force. The force direction is parallel to the cable. And second, away from the chosen body. So a pushing force is a force toward the chosen body. A pulling force is away from the chosen body. We're going to do a lot of problems. So we're going to do a lot of problems that have objects that are rolling or sliding along surfaces, and those surfaces can be at angles or flat or walls or whatever. So here's a general strategy for rolling and sliding problems. Choose a coordinate system with the y-axis straight out of the surface. By the surface, I mean whatever it's rolling or sliding along. That means that the x-axis has to be along the surface. And one of the big benefits of this, we'll see a few benefits as we go on, but one is that that means that the acceleration is always going to have only an x component. So the acceleration vector only has an x component. You can think of it as like a0. And in the math, you can always assume that it's in the positive x direction. The math will tell you the sign if you don't know any more about it. Okay, so let's do some examples. First, let's say that we have a 20-kilogram cart rolling along the ground, and it's in contact with a 10-kilogram cart. And they're both being, or this, there's a 50-Newton force applied to the 20-kilogram cart that's pushing them both to the right. What's the force vector applied to the 10-kilogram by the 20-kilogram? Yep. Thank you. Okay. So we know that we're ignoring any friction or anything like that. So if you apply this 50-Newton force, it's going to make these move to the right. And in order to make the 10-kilogram move to the right, the 20-kilogram is going to have to push on the 10. Okay. And we're going to calculate what that force is that the 20-kilogram is applying to the 10 to make it move. You might think, your first thought might be, well, it's going to be 50 newtons. We'll see that it's not, okay? Because it takes some of that force kind of you can think of as being used up by making the 20-kilogram accelerate. Okay, so the way we're going to do this is we're first going to isolate both of these two as a single system, and we're going to use that to calculate the acceleration. And then we're going to use that acceleration when we isolate just the 10-kilogram. Okay, that's going to be a strategy we're going to use often when we have multiple bodies. So the first thing is a free body diagram of both. And we're going to do this to find the acceleration vector. Well, the strategy that I just gave above for rolling and sliding problems is that the y-axis goes straight perpendicularly out of the surface. So if you're talking about rolling or sliding along a horizontal surface, this ends up just being the coordinate system that we're most used to. There's the x-axis, there's the y-axis. Okay. A free body diagram of both of these. So here's the outline. And we're going to make sure that the weight force is in there, and then we're going to go around the boundary looking for anywhere there's contact with the surroundings, and anywhere there's contact has to be a force. So the weight force is like this, and it's the mass times 9.81, so that's 30 times 9.81. Yeah, so if we isolated just one of them, I'm going to erase this in a second. You don't have to write this down, just look at it. If we, so say that I had isolated the 10-kilogram right from the start, okay? We would have a weight force and a normal force. I'll call that N10. and we would have an unknown reaction force here, and then the free body diagram's done, okay? And then when we went to Newton's second law, you add up all these force vectors, and it'd be equal to the object's mass times its acceleration vector. Well, its acceleration vector is a0. We don't know what a is yet. And so you'd have two equations, an x and a y equation, but three variables, three unknowns. Okay, and so you wouldn't be able to solve it. The benefit of isolating the two things together instead of doing just one of them to start with is that you eliminate all the reaction forces from the bodies from your free body, because now, when we isolated this 10 kilogram part, this pushing force from the 20 acted on the boundary. But if we isolate both of them together, that's not acting on the boundary anymore, so we don't have to deal with it. Okay, and so we're going to have all our x forces, x components of forces known, and then we can calculate a. That's the idea. So when you don't know that acceleration, you can always isolate the two things to solve for the acceleration, or all of them if you have more than two. Yeah, well, both of these things, we're assuming that they're going to be accelerating as a single unit. We're not talking about them bouncing off each other or anything. And so if we can calculate the acceleration for both of them together, then we can use that acceleration when we isolate the single item. Okay, so the force vector is 30 times 9.81. That's the weight acting down. There's contact at all of the wheels. I'm going to lump these all together. So I'll call this N total, the total normal force. Go around. There's no forces anywhere here. We don't have those internal forces because those are happening inside our outline. I was saying that the main benefit of drawing a free body diagram is being very clear to yourself about the boundary between what's inside and what's outside. And all we care about is the forces applied to the stuff on the inside by the outside. So we don't care about the inside applying forces to the inside. Okay. Keep going around, and eventually you get to that 50 Newton force. And that's it. And so now Newton's second law, we have the force vector 50, 0. We have the weight force 0, 294.3, negative. N total is in the positive y direction, so that's 0 N total. And now we've put all of the forces in the free body diagram in Newton's second law, so we know we're done with the left side of Newton's second law. And now this is equal to the mass, 30, times the acceleration, a0. Okay. There's two equations. There's an x equation that says 50 plus 0 is equal to 30a. And so this tells us that a is equal to 1.6 repeating meters per second squared. And there's a y equation that tells us 0 minus 294.3 plus n total is equal to 0. So n total is equal to 294.3 newtons. Okay. Well, we calculated that a, and so now to get the acceleration vector, we're just going to plug that a back into what we already figured out was going to be our acceleration vector, a0, right? We already figured that out. We had to figure it out to put it in Newton's second law. So we knew this was the acceleration vector of these two parts. We just didn't know what the value of a, that variable a, was. Now we know. So the acceleration vector is equal to 1.6 repeating in the x direction, 0 in the y direction. Or another way you can think of that is that's 1.6 repeating, our positive x direction was to the right. So that's an acceleration vector this way with a magnitude of 1.6 repeating meters per second squared. Okay. So that's the way that those two things are accelerating. Any questions about that first step? So now we're going to isolate the 10 kilogram cart and figure out the force that's being applied to it by the 20. So now a free body diagram of the 10. There's a weight force. This time it's 10 times 9.81. There's a pushing force from the ground to the wheels. I'll call that N10. That's not the same normal as we had before because our other one also included the force applied to the 20. There's no force on the boundary as you go around until you get to the left side. And then on the left side, we have a pushing force coming from the 20 kilogram. So it's this way, and I'm going to call it R. Okay, any questions about that?
So why is the 9.81 not negative?
Well, when we put it in component form, it's going to be in the negative y direction. But right now, we're just saying it's this way, and the magnitude is whatever that number is. Okay, and so actually a negative here, this is an important thing to sort of get straight little by little. If you put a negative here, that would be like saying you're taking a vector in this direction and multiplying it by negative 98.1, which would actually mean it was going up. Yes?
Do you think that since it's pointing down, it's already negative?
Yeah, so, right. This is a vector that's going in that direction with this magnitude, and now, based on whatever your coordinate system is, you can figure out what the components are. Yes?
When you did the free body diagram for both of them, why wouldn't the wheels be N20?
They could be. Yep, you could do that. Yeah.
Okay.
So then we would have just had two of them here. We wouldn't have been able to calculate either one of them, which we're not asked for in this question anyways. Yep, that would be a totally fine way to do it. So now we got the free body diagram. Go to Newton's second law. We have a force R going to the right. So that's positive R0. We have a weight force of 0, negative 98.1. We have a normal force of 0, N10. That's all the forces. And these are equal to the mass times the acceleration vector. And this is the acceleration vector. We figured that out in the first step. So multiply this times 1.6 repeating, 0. And now we have two equations again. The x equation says r plus 0 is equal to 16.6 repeating. And so r is equal to 16.6 repeating. That's newtons. And then the y equation says 0 minus 98.1 plus n10 is equal to 0. So n10 is equal to positive 98.1 newtons. Okay, so what is the force vector that's applied to the 10 kilogram by the 20? We figured out the magnitude. Well, if you have a vector with a magnitude of 16.6 repeating in that direction, that's positive x. So it's going to be, 16.6 repeating 0. Or you can also just think of it as like Newton's second law already shows a lot of this stuff. This is the force vector on the 10 by the 20. This is the force vector on the 10 by the ground. This is the acceleration vector. And so if you want to find any vectors, usually it's just a matter of taking a variable that you just calculated and plugging it back into one of the vectors you already defined. So 16.6 repeating, plug it back into this, and you get that the force on the 10 by the 20 is equal to positive 16.6 repeating 0. Or, that's in the positive x direction. So another way to think of that is this way, 16.6 repeating. I mentioned last time that when you have pushing contact, like if we're calculating the force on the 10 by the 20, we just figured out that it's 16.6 repeating that way. What do we know about the force on the 20 by the 10 when you have these contact pairs? Yep. It's going to be the opposite direction, same magnitude. Yep. And we could actually calculate that now if we could figure out that that's true by isolating the 20, going through the same steps. We'd see that we got a pushing contact, the pushing force from the 10 that was 16.6 repeating, just going the other direction. Okay, let's do another one. So let's do two rolling carts again. So let's say we have a 15 kilogram cart on the left and a 20 kilogram cart on the right. And to make a move, we're applying a force of 150 newtons this way. And let's say we want to know what's the force vector applied to the 20 kilogram cart by the cable that connects those two. Okay, anybody have an idea for the first step of this one? What are we going to isolate first? Well, so first of all, if we're trying to figure out a force vector applied to the 20 kilogram cart, you might think isolate the 20 kilogram cart and see what you can solve. But we would have the same problem that we had in the last problem if we would have jumped right into calculating, doing things for the 10 kilogram. So what we're going to do is isolate the whole thing as a system, same as last time, calculate the acceleration vector, and then use that acceleration vector to figure out the force on the 20. Okay. So first, we're going to isolate the whole system. To find the acceleration vector. Okay, so a free body diagram of both of these. There's a weight force that's 35 times 9.81. And then going around the boundary looking for contact, there's a pushing contact from the ground to the wheels. I'm going to lump it all together and call it N total. Like was suggested before, we could also do it as two different ones that we call N15 and N20, and they just add up to be this N total. Keep going around and you get 150 newtons like this. This is a flat ground, so our coordinate system is going to have y up, x to the right. And so Newton's second law says negative 150, 0. Plus 0. Let's see if I have that. Can someone calculate 35 times 9.81? Okay. And then we have that normal force, 0 N total. That's all the forces in the free body diagram. And so all this is equal to the mass times the acceleration that we know is only going to be in the x direction. Which way are these two carts going to accelerate? I mean, just understanding the world. But yeah, it's definitely going to accelerate to the left. Notice that I have it in here. If you can think of it as like my default direction is kind of going to the right. is going to come out in the calculation. So you never have to make assumptions about that. Okay. But yes, when we get our answer, we know that that A value is going to come out negative. We can just see that from looking at the problem. All right, so the X equation says negative 150 plus 0 is equal to 35A. So what do you get for A? Can someone calculate that? Negative 4.29 meters per second squared. The Y equation says negative 343.35 plus N total is equal to 0. So N total is equal to positive 343.35. And so now that we have the value of A, we can plug that into our acceleration vector. And we get that the acceleration vector for each of these is negative 4.290. Or in other words, it's in the negative X direction with a magnitude of 4.29. Are these speeding up or slowing down? It's a trick question, by the way. We don't know. Why don't we know? Yeah, we have no way to know the velocity. They could be starting at rest. They could be moving to the right. The answer for acceleration is the same no matter what the velocity is. Okay, we're going to see that when we start talking about friction, that'll be a different story. But for now, velocity is just irrelevant for these calculations. Okay, and now we're going to isolate the 20 kilogram because we want to calculate a force on the 20 kilogram. So a free body diagram of the 20. There's a weight force of 20 times 9.81. There's a pushing contact from the ground that I'll call N20. There's no contact with the surroundings as you keep going around until you get to the cable, okay? So that cable is applying a pulling force. That means that this force is parallel to the cable, away from the body. And I'll call this capital T for tension. And now Newton's second law. We have the pulling force, negative T0. Weight force, 0, negative 196.2. The pushing force from the ground, 0, N20. And all those, if you add them up, is equal to the mass of the chosen body times its acceleration vector, which we know now. And so the X equation says negative T is equal to negative 85.8. And so T is equal to 85.8 newtons. Question? And then the Y equation says negative 196.2 plus N20 is equal to 0. So N20 is equal to 196.2. All right, well, what we're looking for is the force vector that the cable applies to this body. Okay, so now we take this T value and plug it back into that force vector. And we get that the force on the 20 by the cable is equal to negative 85.80. We didn't have to. I just wrote out both equations, solved for it. But yes, you could skip that step because it didn't ask for it. Any other questions? Okay. That, so if you plug that back into this, it's the normal force. And it's the force vector applied to the 20 kilogram cart by the ground. In this class, we'll always assume that cables are weightless. I guess massless. That means that a single cable applies the same force magnitude and the force magnitude is called the tension. To every body it touches. Well, let's say to every point it connects to. Okay, so now if you wanted to figure out, what we figured out is that the magnitude of this cable force is 5.8 newtons. If you wanted to figure out what the force vector was that cable applied to the 15 kilogram cart, well, we know from the direction of pulling forces that it's going to apply the force in that direction, that positive X direction. We know since it's a massless cable that the magnitude of that force is 85.8, and so we know it's positive 85.80. Okay. Of all the cables in the world, what percentage do you think are massless? 0. But so that might be sort of an unsatisfying assumption. But usually the force that cables apply to things are quite a bit bigger than the weight of the cable. And so even though it's never actually true, you get good results making this assumption in a lot of important cases. Not every case, but a lot of cases. Yeah. And there are other ways, when we go into dynamics and stuff, we'll talk about what to do if you want to include the cable mass and stuff. But for now, we're just going to assume that the weight of the cable is small compared to the other forces it's dealing with. Okay. Any other questions? Okay, I'll give you some problems like these to work on over the weekend. And yeah, lab test tomorrow. See you tomorrow. Oh, yeah. Yeah.